So lately data structures, I actually think you may have at least seen some of the algorithmic techniques in your data structures class, but maybe didn't get around to analyzing it carefully. So that's what a skill we're going to practice today. But usually this class is quite popular, maybe because of some level of familiarity with data structures and stuff. So, okay, so the next theme of our class is going to be a certain kind of average analysis of algorithms. Okay, but it's going to be a very specific sense of the word average. So one is what we'll do today. It's called amortized analysis. And it's going to be these data structures or stuff. They do a bunch of operations, but in hindsight, you're going to see that all the operations have good performance on a per operation basis on average. I mean, we've seen it before with the Fibonacci heaps. We just said, oh, it's like it has a log n delete. It's like it has log n delete. And for our purposes, at the end of the day, we just use the data structure all the way through, so that's fine. But actually, if you had looked at the specifics, some of the deletes could actually take much longer than longet. We haven't looked at the specifics. I don't know if we will. It's partly on me. But uh anyway, so you've at least been using it. And the other kind of average we're going to do, of course, this will be after the midterm, will be randomized algorithms. Okay. But I want to be very clear. The input is going to be given to us by an adversary. I mean, we're going to worry about algorithms that work no matter the input. And we are going to inject the randomization. Okay. So in both cases, we're never going to stray from this worst case analysis. We really want to make robust algorithms and theorems that you can build on, right? You really want strong guarantees, especially when you start building things on top of each other, right? So, so we're never going to slip from that, but there's still going to be a little bit of nuance, because, what I mean by worst case is going to be a little bit more, there's going to be shades of gray compared to before. Okay, but we won't lose any rigor. Okay, and that's almost part of, in as much as, the particular skill of getting good at amortize and the particular skill of getting good at randomize, I think just expanding out a little bit our understanding of what we mean by worst case analysis, that's almost a bigger thing. Yeah. So, um, yeah, we won't do like hardcore randomized algorithms. I'll teach such a class in the fall, but we'll do enough to get and it also, if you like it, maybe you can think of this as like the first lecture or two in case it suits you. Of course, I encourage anyone in this class to take it. Okay. So, one thing I should mention is that both of these will be among the most practical things we'll do in the class. We'll see today how if you use amortized analysis, you can often do much simpler data structures because you're not like, yeah, you don't, we're trying to get worst case for every operation is sometimes excessive. Okay. And you just get more slack and randomized too, just trying to get, things that work well in expectation. It actually gives you a little bit of slack, compared to always being perfect. And then that often permits, well, in interesting cases, it lets you do things you otherwise couldn't do, but also in just very practical cases, you can do these very slick things, that translate well to practice. Okay, so all right, let's start with the most basic thing in the world, right? Like I plus plus. Okay, so you have some integer, and in binary, as you count to 0, 1, right? It's going like this: 0, 1, 0, 1, 1, 1, 1, 0. Wait, that was wrong too? Oh, okay. So yeah, some people weren't here. I woke up at like 2:30 this morning and I couldn't go back to sleep. So so you will actually probably have to fix a bunch of stuff today. And yeah. It's maybe the first time the professor falls asleep in their own lecture. Uh okay, so let's just go carefully. 1, 0, 0. Yeah. 1, 0, 1, 1, 1, 0, and so forth. Okay. All right. So, so you've done this a million times before. You've coded this a million times before, and you've never been concerned about it, right? But still, we're going to ask, what is the running time? What is the worst case running time of incrementing an integer? Oh, what? Yeah, so what would be like a really bad case? Yeah. The one that I failed to do even was 1-1. Okay. But if you have k bits are all ones, how many bits might you have to flip? Okay. Right. So it's not really a constant time operation, even though you've never minded it. I mean, it's partly a constant time operation for you because you've probably never gotten past like k is 32, but like still, it is not really a constant time operation, but we never really mind it. But maybe a more um, realistic question is, as I just count from 1 to n, like you do in your for loop, how many total flips do you do? Because that's probably what you're actually observing when you use I++ in your loop. So, good. All right. So, you have some number. There's a first bit, least significant, second, third, fourth. I think that's the right direction. No, for you, first bit, second bit, third. So least significant, second, least significant. Okay. All right. So the first bit, as you're going I++, how often does it flip? Every single time. So if I call I++ n times, it's going to flip n times. Yeah. Okay. All right. That was the first bit. Now the second bit. How often does this flip? Half the time. Okay. N by 2. All right. First bit, second bit, third bit. How often does it flip? Every fourth time? Okay. Oh, very fourth. Oh, every four times. Okay. And you keep going. The 10th bit, how often does it flip? I think it's not exactly 2 to the 10, minus 1. Yeah. So, okay. So the number of flips is actually going down. Okay. So, good. So in those in increments, you add all these things up. Oh, that was something I was supposed to do. Oh no, it's okay. We add all these things up, right? The first bit every time, the second bit half the time, fourth. So you're going to get n plus n over 2 plus n over 4 and so forth. So it's all going to add to almost 2n. Okay. So in your n increments, you're only spending big O of n time. So in hindsight, it's as if every increment was flipping 2 bits in the worst case. Not actually. Some were bigger than others. But like no matter what, here there's very few degrees of freedom because you can only hit the button and it goes plus plus. But there's no way to cheat it. After 10 operations, you'll always have flipped about 10 bits. After 100, it's not like there's like some random gap where for a moment you're actually flipping way more and then you need to catch up or something. You're always also ahead of this average. Uh, so in this situation, we say it's constant amortized time. Okay. It's as if it was worst case, but it's not quite, and we have to figure out how to justify it. I know a binary counter is very simple, so we're just going to develop a little bit of techniques here, and then we can get into more sophisticated data structures and so forth. So, okay, so that's sort of the definition. So it's saying, look, I'll say some operation takes t amortized time if for any n, if I do it n times, it takes nt time. Okay. And that doesn't mean that every single one took at most t time. And if you have many operations that'll come up soon, you insert, delete, whatever, okay? I might say, oh, this first operation takes constant time, next operation takes log n or whatever. If um, so that would mean that if I ran operation 1 10 times and operation 2 20 times, the total running time will be bounded above by t1 times 10, or t1 is the amortized time for the first operation, times t2 times 20. Like you should be able to add it up, and that should upper bound the total amount of time. Okay? But no matter the order of operations, no matter how many of each, okay, so it should be kind of robust in that sense. So functionally, it's going to give you a lot of what you want from a worst case, but there's a little slack built in as well. Okay, so all right. So there's a couple different ways to do amortized analysis. At the end of the day, you just need to appeal to the definition. So especially something as simple as binary counter, we can just add them all up and say, oh, after n operations, it's big O of n, and we're done. So you can always try to do a direct analysis. Okay. But there's two other techniques which at the end of the day you can show are simulating the direct analysis, but they sort of are metaphors that are sometimes easier to think about. And easier to think about is useful for two reasons. One is, of course, you're looking at something complex and you're trying to analyze it. It's hard to think about. But two is that when you have a better sense of intuition and working model for this kind of analysis, that allows you to do better design, right? Like, oh, I can do this differently and the amortized time will look like this because I'm thinking about some potential function or something. Okay, so every time we get good at analysis in this class, we often get better at design as well because we kind of deepen our understanding. So okay, so let's okay, so we're just going to reanalyze the binary counter to demonstrate these two techniques. Okay, so one is called the credit scheme. Okay, just kind of opposite how credit's used, but anyway, the idea is that you can buy credits ahead of time to pay for. So the algorithm is doing work at each step, but maybe in uneven chunks. Flips one bit here, but then flips 10 bits later. Okay, and the idea is that uh, you can buy credits and say, oh, I'm going to buy like 1 unit of work and kind of pay up front, like, oh, I'll charge an extra unit of work right now. And then later I can cash that in when the work gets bigger. Okay, so the idea is like, oh, this increment was very easy. I only flipped one bit. I have room to buy a few extra credits. And hoping once I get to flipping 10 bits, I have enough credits in the bank to account for it. Okay. Okay, so the idea is this. So we're going to come up with some uh, given your data structure, say the binary counter, you're going to come up with some scheme for buying credits. And you can be clever. You can buy fractional credits. You can allocate and organize it in some way. Say, oh, I'll buy, you know, an example will clarify this. Okay. And so you're always going to pay in each iteration the running time plus a net change in credit. So maybe you're buying credits in an iteration. So it's some constant work, but I also bought log n credits because it might be useful later. And then maybe later on you have this big heavy operation, and then you're going to spend some of your credits. Okay. But you're hoping that the credits will offset the running time, the true running time of that operation, so get you back under whatever you want for amortized time. Okay. And if you could do something, follow these rules, it's not hard to kind of compile it into a direct analysis. Okay. In fact, I do it in the notes, but today I just want to focus on using these more than they're pretty straightforward, but okay. So I know I've only explained it abstractly, so it might be hard to apply, but still I want to give you a chance. So binary counter, we already know it's constant amortized time, but I want to try to come up with a credit charging scheme. Okay. So, each time you try to increment, you also buy some credits or something. Somehow you want to, yeah. But any ideas? Yeah. Yeah, so in principle, if you buy 2 credits, that should be enough. So maybe the trickier part, because it's amortized time, it should be 2. And you know that in hindsight. Maybe the trickier part is, how come when you flip 10 bits, you have enough credits in the bank without maybe going all the way back to that full table we did? Like it would be nice, for example, if I could, imagine like if you're saving money for buying various things, you might have oh, I want to save some for this and I want to save from I don't know, what do people spend money on anymore? E-cigarettes? I'm kidding. I only read stuff in the news. Okay. But you could potentially sort of set up various accounts so that some particular operation, once you do it, you can argue that account for it has blah, blah, blah. Like it would be very nice, you have many bits. It'd be natural to maybe have an account for every bit and make sure that whenever the 10th bit flips, there's one full credit in that account. And same as the 20th, same as the first. So as you buy those 2 credits, it would be nice if you came up with a clever way to distribute those 2 credits. You can divide things too, right? In a way and try to argue that, oh yeah, when I'm flipping a 20th bit, by then I should have accumulated 1 credit. I think it's maybe a little hard because we haven't done one before, but yeah. Okay, so the least significant bit. Oh, okay. Uh, okay, yeah. Can you move? Okay, so he starts with 2 credits, he flips and he moves one over, and now this guy flips every once in a while. And but then is that what happens to that 1 credit? He moves again, or are you going to spend that credit? But then what credit are you using to spend to justify flipping the second bit? Well, so we are trying to prove something I think we all understand. But right now, this version of let's keep moving these credits around just when we need them, it's not 100% clear that we're not like, creating credits out of thin air. I just want to make it a little more clear. Uh, and there's other ideas that maybe will make it more solid. Yeah, so that will be 1 credit, but you're gonna buy 2 credits, so you still have 1 more credit. So okay, so we'll buy 2 credits. First bit will definitely get a credit. It's going to be used to flip that bit. What should I do with the remaining credit? Okay, but how am I going to like clearly argue this works? Okay. Um, but remember, you can put fractions of credits. You can divide them up. Does that help? So in the second bit doesn't need a credit every time, right? Oh, okay, so it needs half a credit every time. So how about the second bit? The third bit? Are you a fourth every time? Yeah, so that every time the clock strikes midnight every 4 times, you have a full credit. This is only the analysis. So we don't actually have to create credits. Yeah, there's no ledger, there's no hashing. Oh yeah, yeah. So let's go through it. So all right, so how many credits on the first bit? How many on the second? How many on the third? How many on the ith? Something like this. Add it all up, you're spending 2 credits. I mean, it's obviously the same mathematics as our previous table, but it's just organizing in a different way. And some people find this easier to think about. Yeah, once I get around to the 10th bit, it's been 2 to the 10 increments, and I've collected 2 to the 10 bits of 1 over, yeah, right? Okay. All right, so that's this credit idea. Again, this might be so simple, you're like, why bother? But still, but the idea is clear. All right, good. So the only rule is that you can only spend credits that you've already saved. And maybe the challenge is just coming up with a clear scheme so that you can argue that you always have credits in hand. Yeah, I mean, doing this one half, this fractional allocation is much easier to think about than this kind of like crazy Go game of like, oh, this hops over the other, and then like do not pass Go to not collect $200 or something. Okay, all right. So another one, which many people always know is implicitly kind of similar, is the potential method. Okay, and you can kind of think of your bank account as a potential, but still, some people find the word potential useful. So. But maybe the style is a little different. Often, like your potential is some kind of description of your data structure state. So it's kind of easy to read off, like your data structure is in some state and the potential maps to this. And then your data structure updates its state. Okay, and it might take some work to do so. And the potential changes. Okay. And what you want is you want the change of potential to offset the real time you spend. Okay. So when you have a really big operation, so basically, I mean, it's just like physics potential, you push something up a hill and now you have this stored energy. Okay. And so what you're hoping is that when you have a big expensive operation, like, you're doing some big garbage collection, it cleans things up. And if your potential is measuring garbage, then the decrease in garbage will offset the work you spend cleaning it up. Something like this. So this one is maybe the least popular initially because it feels the most abstract. Um, Often it leads to the easiest proofs because if you can find the right sentence capturing the potential, then it's like very easy to verify. So I feel like I often maybe like first think in terms of credits, and then like when I'm lazy when it comes to proof time, I think of trying to turn it into a potential because it's easier. But you can choose whatever you want, of course. But this is another one. So okay, so again, the first time we do this might be a little awkward. So, but still, so for a binary counter. I want to come up with some kind of potential. It's something that describes the state. And I want this quantity to maybe go down when I'm flipping a lot of bits so that offsets the bits I flip. Okay. So suppose we set the potential here to just be in our current counter, the number of bits that are set to 1. Because whenever I increment, only one number goes from 0 to 1, and the rest are going from 1 to 0. So all those that are going from 1 to 0, every time one goes to 0, the potential also goes down, and it covers that flip. And at the end, you have to flip 1 from 0 to 1, so you pay for the 1, and the potential goes up by 1, so you're paying 2 total. Okay? So this might be a little bit, in various situations, it might be harder to divine this sentence, number of bits set to 1. But if you get the right sentence, then sometimes it's very easy to verify that it's correct. All right, so those are the three main things. Okay. And then now we have more interesting examples, and we can choose whatever method we want. We'll probably do all of them, I guess, since we're friends. Okay. But any questions at this stage? All right. Okay. All right. Okay. We always use arrays and array backlist, right? So what's great about arrays? Oh, one access time. Okay. Now, what's bad about an array backlist? Ah, okay. Yeah. You run out of space. Now, what are you going to do on the n plus one? Okay. So do you guys know what they do? Yeah. It's called the doubling trick. Okay. So you allocate an array twice the size, you copy everything over, and you add one more. Okay. But obviously, you're copying n things just to append one. So from a worst case perspective, this is not great. So the question is, how do you justify this? Because everyone does this. If it was so bad, they wouldn't do this. Maybe they would because it's also simple, but eventually someone would point out it's a bad idea if it was really a bad idea. Yeah. Yeah, so the idea is that, you add this big buffer and then you have to fill it all up again, right? So we just want to do an amortized analysis. And so I think you've all seen this to some extent in your data structures class. So maybe the exercise here is let's just get it down on paper and do it correctly. So, okay. So yeah, with a doubling trick, you get append in constant amortized time. Okay. We can prove it any way you want to. We can come up with credit schemes. We can do a potential method. So this would be a potential. Okay. Phi equals number of empty slots at the end or something. Okay. So now append. So like normally, if you're not doubling, you're going to add one. So the phi is going to go up by one, right? Oh no, phi is going to go down by one. Plus you're going to do constant work to add one more thing. So that'll be constant amortized. Okay. But now what happens when you double? So if you double, phi actually goes up by n, and you also pay n work. Uh, this actually looks like O n amortized. What you want is the potential to go down when you're doing a lot of work to offset. Okay, let's try non-empty slots. Okay. If I insert one, I lose one non-empty slot, and I pay O1, so that comes out to O1 plus O1 is O1 amortized. Okay. Now, uh, okay, now when I double, what happens to phi? Phi goes down by n. Does the number of non-empty slots change when you double? So phi doesn't go down. Okay, so the one rule about of the potential is it needs to be non-negative. Because otherwise it'll map to kind of like stealing credits from the future. Okay, maybe, oops, number of non-empty divided by n. Okay, so normally phi will go up by like 1 over n. And then what happens when you double? Yeah, it goes to phi over 2. And it's at most 1, so it goes down by half. So you get half a credit kind of to work with. You guys want to try a charging scheme? Maybe get better luck? Okay. All right, let's try a charging scheme. We'll come back to this. Okay. Any ideas for a charging scheme? Okay, to just pay 2 credits with each append. Okay. And then you're paying extra O1 work. So now what happens when you double? When you double, you have to copy n things. And now you want to argue you have n credits? Yeah, actually, it's not exactly n. Yeah, so this comes after n over 2 appends, which will give you n credits, and that will pay for copying n. Okay. And in general, we're not too worried about constants. So if you wrote pay 1 credit and then each credit is helping you move 2 items later, that's not too big a deal either. But 2 credits might be easier for someone reading it just to get a sense of what's going on. Okay, so that will work. Good. Do you want to try again at the potentials? Sorry. Oh, uh, well, a potential that's more interesting than effectively saying number of credits I've stored if I use the exact same. Well, okay, so ideally what you want to do, so okay, so the question is, okay, can I make phi equal to the number of appends I've done so far or something, right? But first you have to be careful. When you double, the potential won't go down. And then you can say, okay, minus something for double. But the other thing is that it would be nice if so when you get a nice sentence character like number of bits that are 1 or 0, which for a binary counter doesn't seem very interesting, but for a data structure with multiple operations that are being used, and again, this is only one operation, but you can insert and deletion or something, then, if you do something that's sort of based on the exact operations you do directly, then it sometimes it can get complicated when, oh, did I do insert and delete or insert delete or insert delete delete? You get a lot of path dependency if you're not careful and stuff. So it'd be nice if we can come up with it still would be nice if we come up with one clear sentence that, yeah. Oh, okay. Um, Number of full minus number of empty. Okay, so normally the potential will go up by 2 because you lose one and you gain one, so you get constant amortized time. Okay, now what happens when we double? Right. Oh, because we're going to gain a bunch of empty slots. Uh, oh, and the number of full won't change. Good. Something like this. So the potential will go down by n because the full hasn't changed, the same number of full, but the empty will go up by n. And in this particular case, our arrays are always at least half full. Oh, assuming you start at like a empty array or something. Maybe with a non-empty, so maybe like you can add like +1 or something. Okay. Uh, yes. Okay. So handling that minor detail, I think this would work though. And this is kind of easy to read off. Oh, yeah. You do need to make sure that phi is non-negative. Sorry? It's true. But what I'm particularly concerned with is that phi go down enough to pay for the doubling. So it is true that phi goes to 0, but the point we're particularly concerned in is that phi went down by n because that n is going to pay for copying things over. Yeah, it's just a point of emphasis. How's your psych test? Oh. How's your psych test? Oh. No, just kidding. Okay. All right. So is that okay? So that's one potential that would work. We're doing amortized analysis today. All right. Okay. Good. All right. So much for array lists. If we have time, we can do it as an exercise incorporating deletions. But okay. Next thing, search trees. You guys also did this in your data structures class, right? So we're just going to do search trees. The only rule is the keys on the left are smaller, the keys on the right are bigger. All right, so, and as you know, search trees facilitate a bunch of operations. Is there a key in there? Okay, I think I have this set up. So, for example, uh, does the tree contain the number 7, right? Oh, yes, that's right. It does not. But but how you start at 10 and say, oh, 7 is smaller. You go to 5 and it's bigger, and it's 8 is smaller, it's 6. No, it's not there, right? So there's no 7. This, of course, you know. All right. Another operation is something like list all the keys between 7 and 18 or something, right? And so you kind of crawl down the tree in the same way, and then you kind of say, oh, I'll go back up the tree and I'll check all the inner branches inside, right? And same as like for 18, you kind of find where 18 is in the tree, and you're going to make sure that you visit everything sort of on the inside, which is not so bad with some care. Okay. All right. So this you've also done. Okay. Suppose you wanted to do something like how many keys are between 5 and 25. Of course, you can list all the keys and count them up, but you can do a little bit more efficient. So you want to count the number of keys in some range. Yeah. Yeah. So I think that would work. And I find it easier to just write down here in green how many nodes are just in the subtree. Okay. And now when you trace the same paths, those inside subtrees, you don't have to traverse all of them. You just look at the head and say how many nodes are in there, and you add those up. Okay. And this way you don't have to do things proportional to how many keys, just the length of those search paths. Okay. So, yeah, kind of standard tricks. Um, The main point of all these things is that the operations always take time proportional to the size of the tree, right? Or sorry, the height of the tree, just how long it took you to get to a leaf. Okay, which means that you can have two very different characteristics if the tree is very balanced or a tree is, of course, completely unbalanced. I'm sure this was preached to you to death. Okay. Now, the most natural method for insertion, if I'm inserting an element, is just insert it as a leaf, right? So if I'm inserting 7 here, then we figure out where it should be, and I'll put it there as a leaf, right? Uh, but I think as you all know, this may lead to a balanced tree, but it might not. So something like to generate this worst case, what would be an insertion order? Ascending order. So if you inserted 1, 2, 3, 4, 5, 6, 7, then you insert 1 first, then 2, then 3, and so forth, and you get the worst possible tree. And the saddest thing is, this seems to be a very plausible insertion order as someone fills out their database or something, right? They just go in alphabetic order and they ruin your silly tree. Okay. So, all right, you guys actually probably have a bunch of answers for this. How can you keep a tree balanced? What did they teach you? Red, black tree? Is this where some nodes are like red and some are black at any point in time or something? Huh? Oh, randomized? You guys really did that? Well, first of all, there's something called a randomized treep, which works quite well. Do you guys know what a randomized treep is? Or maybe I'll save it for a randomized lecture then, or for homework. Not to get too excited. Okay. What would did they teach you anything besides red black trees? Huh? 3 trees. Oh, 2, 3 trees. How does that work? Does that sometimes have like 3 children? So if one gets bad, they start splitting things up or something? Okay, 2, 3 trees. Yeah, so what are some other self-balancing trees? AVL trees? Any others? Do you guys do scapegoat trees? Okay. Does anyone remember? Can anyone actually explain in detail how any of these trees work? Red, black trees, 2, 3 trees, AVL trees. It's something complicated, right? Yeah. Okay. So, all right. So today we're going to do something that maybe you guys haven't exposed to, but we're going to be very, very lazy. Okay. We're going to do the laziest possible thing. Okay. So we're just going to insert at the leaves. We're not going to do any of this red, black tree nonsense. Okay. We will keep track for every node how many children it has. So I can start to tell if like things start to look wonky because one child's way too big or something. Okay. And as I insert things, maybe I find that one subtree is much bigger than the other, right? Because I'm not doing anything because I'm lazy and I didn't pay any attention in 251. That's the number, right? 251. Okay. All right. So what should I do when it's unbalanced? Yeah. That sounds hard. All right. Who's got an easier answer? We'll just rebuild a new tree. Yeah. So I'm just going to rebuild the entire tree so optimally. It's not very hard. The elements are even already in order for you. So you can just lay them out and say, oh, this should have been in the middle, and then, right? So just rebuild the tree whenever it gets really bad. Yeah, this is like how do you keep your room clean? Just clean whenever your parents finally ask, right? It's never actually clean, but it's clean as far as they can tell. So whenever it starts to get unbalanced, okay, finally I'll fix it. That's all. Okay? So I can't imagine doing less work. All right. So we're going to try to prove two things. We're going to show that the height is always at most log n. You need that as a preliminary thing. And then we'll show that all your insertion takes log n time, amortized time, which is great, right? Because it is relatively simple. Okay. But it is important to at least understand why the height is nice and small. Okay. So why is the height of this lazily balanced tree always at most log n? Yeah, off by 1 bit. But even if I went to the bigger side, at most it has 2/3 of the nodes. So I'm getting rid of 33% every time. Maybe not half, but still a constant fraction. So you're going to get log n depth. And we're always enforcing this. Okay, so you always have log n depth. So that actually comes for free. So the interesting question then is why does insertion take log n amortized time? Sorry. Why does insertion take log n amortized time? Okay, so uh, do I have a good picture? Okay, so all right, so first of all, you guys seem to like potential, so we'll go like that. So I have some kind of tree, okay, and there are a couple suggestions. One is the height of the tree. Another suggestion was like height of left versus height of right. But that also brings up a question: the biggest height minus the smallest height. of, oh, sure. But one thing I do want to point out is that, okay, there is a left and right child, but they have left and right child, so it's not 100% clear what you mean by right. And like, you know, like, do you just want to do like maybe deepest point of the tree minus shallowest, kind of? Okay, so I'll put in parentheses, assuming we kind of understand kind of deepest minus shallowest. Okay. And just I want to quickly note, these are both going to be on the order of log n, right? Because the height's at most log n. Okay. Do you have another idea? Okay, so this is a different idea. What if every single thing had its own potential? And then the potential of the whole tree will be the potential of all the subtrees added up. Why does that seem appealing? Yeah, so this is occurring at every subtree, although maybe it wasn't drawn that way. Okay. So this is just part of some other tree. And it would be very nice when we're kind of working in this space, have some localized potential to pay for just this operation, and it won't affect the other things and stuff, right? Okay, so on a per subtree basis, what did you think was a natural? Yeah, so maybe phi is equal to the absolute difference in subtree size, something like this. This will always be greater than or equal to 0 because it's an absolute value. Okay, so in this example, the difference will be 50 because I have 100 on one side and 50 on the other. Okay, and then we'll do that for every tree. Okay, so now let's break down the insertion into insertion and then afterwards rebalance it. So the first thing you do is insert, right? So you're going to go through a tree and you're going to crawl down the tree or something like this. Or maybe it'll be more fun to go on the rebalancing side, something like this. Okay. And as you do, you're going to increase some of the potentials because or at least adjust some of the potentials along the way. Right. Okay. So each of those individual subtree potentials, how much could they go up by? One. Okay. But how many could there be? Log n because the height is log n. So we'll increase the overall potential by log n. That's not bad. Log n's a good number for a search tree, right? Okay. Now when it comes to rebalancing, say this particular tree has potential 50. And then when I rebalance it, what does the potential become? 0, maybe 1. It only takes 50. So you're going to have your potential is going to be proportional to the total number of nodes. I guess it'll be like a third or something when it reaches that point. And it takes linear time to do rebalancing, especially since everything's already sorted. So the change of potential is just going to pay for this. And in fact, probably little potentials on the inside might go down too, and you're not even getting credit for that. Because all those little subtrees might have slight imbalances that you just automatically fix when you rebuild the whole thing. Okay, so you say, oh, okay, I was paying for the imbalance up front. Was the potential going up every time? So it'll pay for fixing it, yeah. Yeah, but that sort of makes, so this subtree, and say the little fixed n to be like 200, right? You need to insert 200 elements before it even gets, or 100 elements before it even gets unbalanced. Okay, so what we kind of want to do and amortize in these situations, right, is we have these data structures that every once in a while do some heavy duty cleanup or heavy duty doubling or something like this, right? Most of the time it's doing little stuff and it's not, in fact, our algorithm is mostly not doing anything. You insert, just insert as a leaf, insert as a leaf. You're doing nothing. but you're accumulating a little bit extra log n extra time. And what this amortized algorithm and analysis is trying to let us do is justify, by the time I do this big operation, I've actually kind of saved up time from early operations being fast. So it should be unintuitive or surprising. How do these log n's add up to n? But then we can look at what's going on in our potential. So let's say that at some point the tree has 100 elements, is perfectly balanced. It just got balanced, the potential is 0. And so that means 50 and 50. To get to another state of unbalance, you have to at least add 50 here or 50 here. And so every time an element comes, the potential for this particular subtree might go up by 1, go up by 1. By the time you get to 100 versus 50, this potential's gone up by 50, which you've already paid for along the way, because you've added 50 elements. Each of those quietly, we're just putting one more drop in a bucket, one more drop in a bucket. So it's very slick, but it's doing the accounting for you, so that when it comes to time to finally do some heavy lifting, you can say, but I've already done insertions proportional to the work I did, and I can charge it off. Yeah. So this is going to actually be, well, okay, so the rebound, so worst case runtime is linear because the elements are already in order, so you can just traverse the tree and lay them out in like an array. Then pick out the middle, that should go at the root, and then you build the left and build the right. So you don't have to sort again. Otherwise, it would be a little messier because you have to pay n log n. So, right. And then as far as the amortized time goes, the rebuilding, which is part of insertion, is just paid for by the potential. So you get log n amortized time for each insertion for a relatively simple algorithm. Uh, I think it's going to be pretty small. I would, because not only that, but I think for example, if you kind of know that things are um so at some level, like something like an AVL tree or red black trees, I feel like each insertion you have to do a lot of writes because you're adjusting all these things. And I would prefer to just do a bulk readjustment from a computer friendly point of view. So I don't totally know in the sense that I haven't done these recently. Also, like once you get into practice, you'd rather do B trees. I would do a lazy rebuilding B tree or something in practice. Um, I think databases would prefer to like also rebuild when everyone's not using the database and things like this, right? So, but yeah, my this is not formal. My thought process for like what translates well to practice is it simple? Usually the simpler things do reasonably well. Like it's like remember our median of means, very clever algorithm, and it doesn't do so well. It's working too hard, even though it's linear time. We'll do something called quick select soon that's much faster in practice. Yeah. So I don't know. You can test it. I'm not sure also what would be a robust test data, but yeah. Okay, good. But yeah, I feel like this would be kind of pointer friendly as well. Okay, so that's login insertion. All right, deletions. So you might remember from red, black trees, AVL trees, whatever you studied, deletions is like insertion times infinity, right? Like in terms of being a mess. So how do you typically delete from a binary search tree? You want to delete 7 or something. But usually you first search for the key, right? And if the key is not a leaf, what do? Nobody knows. Okay? It was one written on a stone tablet. Okay. So we're going to try to do the laziest possible thing, which was suggested. Okay? Uh, when you want to delete a node, I'm going to find it, and I'm just going to check it off as deleted. I'm not going to bother restructuring the tree. Uh, I'm going to wait until half the nodes are marked for deletion, and then I'll rebuild the tree. So I'm going to do garbage collection, basically. Okay? Much easier than yeah. Okay. So that's the idea. Okay. All right. So the idea is that lazy insertion and lazy deletion take log n amortized time. And now we need to justify it. Yeah. Couldn't you just replace it with the successor? But then what if the success, see, you get into this nonsense, right? And it's like, okay, now here's the successor. Okay, now you have to replace the successor with a successor. Yeah, you can. It just, yeah. Okay. All right, we're just gonna mark up, yeah. Okay, phi equals number marked minus number unmarked. Okay. I think that'll be fine. Unmarked minus number marked. Any other ideas? This will, I think, work, but there's like a slightly easier one. Just number unmarked. Yeah. Now, one thing you want to be a little bit careful about is that you do need to kind of argue that these are all log and amortized jointly. Because like removing marked things can affect the unbalance. You also have to figure out what you mean by balance now. Is it number of nodes but on each side? But then are you counting the marked and unmarked? Yeah, you probably want to count them, right? So you want to first, so in other words, we'll have a couple of different potentials going on. So one will be the potentials for balance like before. So for every, maybe here I'll use a different symbol. I'll use psi, okay? And then before, for every node V, we have the absolute difference in size of these subtrees, which includes the marked nodes. Okay. And so you have to redo a little bit, okay, but it's not going to be so bad. When you rebuild the tree, you still have a large potential to pay for it. Okay. And it's your rebuilding will be adjusted because you can filter out some of the marked things along the way. You know, you can delete them while you're rebuilding. And that's not going to hurt you because that's only going to decrease the other potential. You might need to be more careful if you're increasing the other potential, right? Because then it gets a little weird. But in this case, doing this cleanup here only helps clean up the other thing, so it's okay. So you reestablish that argument, doesn't change too much. And then now you move on to the deletion. When you clean everything up, you know, you certainly half the tree is marked for deletion. So it'll be easy to pay for rebuilding the whole thing. And as you rebuild the whole thing, as you clean things up, you get perfect balance everywhere. So all those other potentials will not increase. But it is at least worth noting that these things can't be taken completely separate. At the end of the day, there's sort of always a total potential that's summing everything up. And so you want to argue that whatever the operation, the running time is offset by the total potentials going up and down. Yeah. Well, the nice thing about the potential, so you do need to make sure your potential is defined a way that it's never going to be negative. Because negative would be kind of like stealing. you're always fine. So you don't really have to fully, you can just say, oh, wherever I am now, the sentence gives me this description and I can just trust it. Sometimes so that's the nice thing about potential, especially from a proving standpoint. If you just capture that sentence that captures the state and you can cleverly charge it off, it's often very easy to prove. Sometimes when we think algorithmically, I think it's natural for people to think in terms of credits, like, oh, I did this, I paid a credit. We could have done credit arguments where you put credits on the nodes, you put credits on the marked vertices, and it would have been okay. So as a vertex goes down and creates imbalance, I'll put one credit on each of the roots to pay for balance things later. I mean, it's very similar to how the potentials are working. But the potential way, you don't have to quite worry about, yeah, some of the causality, I guess. Okay, how are we? Okay, good. All right, good. So that's log n amortized, but insertion deletion, easy cake. Is that a phrase? Easy peasy. Okay. All right. Good. You're gonna insert and delete at the same time? Just rebuild the whole thing optimally. Well, I think we'll just redefine rebuilding as both bounds and cleanup, whatever subtree you're in. But personally, if you can pay for rebuilding the whole thing because you have enough deletions, I would just rebuild the whole thing. But I think this is a good position to have because you're in a situation where you have plenty of credits. You have plenty of credits from a insertion point of view and balancing point of view, and you have plenty of potential from a deletion point of view. And all you're saying is, one of the operations will suffice. So I think it's okay. They only go down because you're rebuilding optimally and you're removing things that were marked. Yeah. So you're gonna get perfect bounds. So it's okay. Okay, good. Um, good. All right. Okay, so I think did we talk about immutable data structures once before? Okay, I think I was talking to Peter about it. Okay, so does anyone recognize anything in the bottom right? Okay, yeah. Anyone done this book? Oh, yeah, the website. I mean, it's great. Okay, what about the symbol in the top right? No, it's not the closure symbol. You guys know what closure is? Huh? Closure, it's a language. It's a Lisp that runs on the JVM, but it also tries to be purely functional. Okay, so these are all functional programs. So anyone mess around with functional programming languages? Well, there's this class, right? Ben teaches. Okay, yeah. Okay, so first of all, it's really fun to program in a functional programming language. It imposes certain rules for various reasons, and you have to work your way around it. And it's a little annoying at first, but it's also an interesting experience. Um, so functional programming languages, I mean, part of their goal is to make things look like math, right? And like once a variable has a value, what they want to think about is in terms of values instead of variables. Like variables are memory locations you can rewrite and stuff. But in math, you just have some value, 5, 7, right? And they want to kind of treat it like that. So they have this rule where once you write something, you're never allowed to write over it, ever. Okay? Which seems quite cumbersome. That means you don't have arrays at your disposal. Okay? So you have to kind of like do these hacks and break all the rules, but it's okay. Um, so obviously that's quite restricting. And you're like, why would I do this? So there's some benefits. Does anyone know or can think of some benefits? Why would you want this? You could put it in a set. Yeah, well, there's some consistency at some level, right? Because once you have something written down, no one else can mess it up, right? So there's okay. Yeah, so no side effects is one. Okay, so they want to do this purely functional code. When you do something, I want to compute f of x, and you don't want it to mess up some y somewhere else. And the rules say you're not allowed to mess up with any other y. It's just going to return some value and no state changes. right? So if you have a system like this, it's much easier to reason because things won't mess each other up. Okay. Um, so one great place for this is concurrency, right? Because the whole problem with concurrency is everyone writing to the same location and state changing across processes. But if state's not allowed to change, if I have a pointer to this, no one will ever change it ever again. Okay? And what happens in practice in functional programming language is that it isolates the one bit of state you want to actually share very cleanly, and then you do some hack there. I mean, they call it a monad, but it's okay. All right. So, but it definitely cleans up concurrency is like very painful, right? Like it's just impossible to do anything well concurrently. Another one. It helps the compiler. When the compiler can make strong assumptions, it can be more aggressive. So in fact, Haskell often it's a very strongly typed language. So compiler gets lots of information and it's still garbage compiled and all these things, but it actually, for a lot of benchmarks, can perform very, very well. Um, and some of these things, your code won't rewrite to the same location, but then when a compiler figures out when it's safe, it'll actually inline some of this for you. Okay, do I have any more reasons? Nope, that's it. Okay, I'm sure there's more. All right, but at least those are some of the ideas. Okay, so an example of an immutable data structure from Lisp in particular is a linked list. Does anyone know what it's called in Lisp? First of all, do you know what Lisp is? Do you know how old Lisp is? Okay, who thinks 60s? 50s? Yeah, what year? What year was Fortran? I think it's 1 year after Fortran. At least McCarthy's paper, I think, is 1 year after Fortran. Okay, but super old. It's even though it's from the 50s, from 58, I thought. I recently had it on a slide. It had garbage collection, it had lambdas, it has like everything, right? It's unbelievable. So, but in Lisp, I think they were, for example, they were doing on cards or something, so things were awkward. But they have these cells called const cells. Okay, each const cell has two pointers. One is called the car. Again, I'm not quite sure why these are, and the other one is called the kadir. Okay, and so these are the basic objects with which everything is constructed. So the original goal was to make things as minimal as possible. I think he actually wanted this the most minimal Turing complete language so that because once you have a programming language, then you could do things, yeah, like anyway. Uh, okay, and the idea is that somewhere down here is your piece of data in a linked list, and the Kadir will point to the next node. Okay, so they're just words for something you already knew. All right, but these are of course very old ideas, and the idea was, oh, let's just make a language that in particular can do this very fluently. Because pointers are already a big deal in the 50s. Right? McCarthy was, I think, motivated by doing like symbolic calculus, just taking derivatives, x squared becomes 2x. So just symbol manipulation. So he needed something. He wasn't doing numerical calculations, right? So he can't just deal with arrays and matrices. He needed to actually, yeah. But obviously this is the kind of language we use now, right? Python is just Lisp in disguise. But in terms of like adopting all of its ethos, it's obviously garbage collected, dynamically typed, all these things. Okay, I'm ranting. Okay. So if you can't change anything that's written and you want to actually change your object, I have an object with two fields A and B. Okay. You have to actually copy the object entirely and replace that field. Okay. So here's some object A, and you replace B, you actually have to copy A as well. You copy the whole object because you're not allowed to write to the same location. So you make a new object and you have a pointer to your new object. And that might seem bad because like objects can be big, right? But what happens is that a big object often looks like this. A big object really looks like pointers to lots of other objects. It's not usually just one struct with tons of fields packed in. Okay. And in a situation like this, even after I update B in this copied object here, okay, and it's like, oh, do I have to, recopy everything else? right? All these sub-objects, but you don't. You just create pointers to these things. You don't have to copy the objects, the sub-objects. You just copy the pointer. So you don't have to rebuild the whole big complex thing. You just have to rebuild this node in your object system. Okay, so that's okay. Where's the amortized analysis? So we're going to try to implement stacks and queues under these severe rules of you cannot rewrite to any location. Okay, those are, I guess, pictures of stacks and queues. All right, stacks. How can I implement a stack immutably? Yeah, so what does that really look like? It's just a linked list. So if you have a linked list, then whoever's using the stack just has some pointer to the head, and the linked list just points down. If I want to push, I just create a new node, and I point to the top of the previous one, and whoever's using the stack has the pointer to the new head. If I want to pop, what do? You don't delete. You're not allowed to delete. You just point down. This way, someone else using the stack, nothing has changed, right? So that's kind of neat. Okay, so very simple. How about queues? How do you do a queue? Okay, can you do a linked list? So if I copy this linked list, that's not copying. If I copy this linked list, right, and I keep a pointer to the head, and I keep a pointer to the bottom or something. Okay, I can imagine pushing on top, that'll be just like a stack. But how am I going to remove from the bottom? Oh, okay, how would I use two stacks? Okay, uh, okay, so you wanted another, something like this, but you wanted, all right, let's see if this works. All right. Okay, so you wanted two stacks. Are these supposed to be the same object? Okay, so the top corresponds to each other? Okay. So now how do I push something on top? Okay, so if I push something on top, I can imagine creating another thing. Oh, oops. I can imagine creating something on top or something, right? But how am I going to update the other? How do I update the other one? Ideally, you'd want to put it up here, but you can't do this because that node's already set in stone. Okay, so okay. So what we're going to do is something like this. We're going to have two stacks. So those are all different items, even though they all look like the same blue square. And one is a stack that you push things onto, and the other thing is a stack that you pop things out of. Okay, so one's handling the in, one handling the out. And of course, the interesting case is what happens when the out gets empty and everything's on the inside? Just flip things over. Okay, so when you're in a situation like this, you're going to flip everything over. So you're in this situation, you want to pump something else out. So it'll be like this, but the letters will be reversed because it's a stack. Something like this. And now, you did want to get rid of A. A was at the bottom of the in stack. It was the longest to go inserted. And now it's right on top of your out stack. Okay, so you flip everything over. Oh, yeah. Okay, so in a word, how do you argue this is justified? Yeah. Yeah, we'll just put a credit on each one. Yeah? I push it, pay constant time, put an extra credit there. That'll pay for flipping it over later. Yeah. That's it. Potential could be the size of the in stack. That would be fine. Okay. So sorry I went over. And that's it. That takes constant amortized time. All right. Good luck with the midterm and shoot me an email if you have any questions.